These are in listen-only mode.
Hello,
Hello.
good afternoon, good evening, and good morning. It's a great pleasure to welcome you today to our second webinar of 2015. The Indian nation has lost one of the greatest mentors for our generation, and we at APQI deeply mourn his departure from this physical world. As a mark of respect to the departed soul of Dr. Kalam, I propose to observe silence for 1 minute. We will miss him very dearly. In increasingly digital world of today, the sensitivity of plants, process and equipment demand for high power quality environment. And poor power quality can impact severely both in terms of economics and safety. Asia Power Quality Initiative, APQI, is an independent platform that aims to build awareness and capacities on issues related to power quality. This pan-Asian platform, supported by national support network partners, continues to carry out activities towards capacity building and awareness creation amongst various stakeholders. We work further to facilitate regulatory and standards initiative in a respective country. We provide a neutral platform for exchange of knowledge and best practices concerning power quality. Our website www.apqi.org, supported by Leonardo Energy Europe, is the single largest resource for discussion papers, research and data on power quality in all the countries we work. We work with a focus on shared learning, transparent exchange of information and active engagement in this field. I welcome you all on behalf of APQI India to this webinar, Reactive Power Compensation in Harmonic Rich Environment. We are quite familiar with reactive compensation, but in nonlinear load dominated world, it has assumed a different proportion altogether. Many of us in industry complain about failure of already installed capacitor banks when we have gone ahead in implementing varieties of energy efficiency measures. Our distinguished industry and utility experts from TDK, APQI, and Reliance Infrastructure, earlier Reliance Energy, will talk about various issues we face in harmonic rich environment, especially while doing reactive power compensation for better power factor to avoid penalty or reducing energy bill. We will learn how and what to look at while deciding reactive compensation in harmonic enriched environment. Some real-life examples are also there to underscore the need of addressing harmonics. Dr. Venkatesh Raghavan, President Power Quality Solutions, APQI India Private Limited, has over 26 years of industrial experience and 2 years of academic experience. Prior to APQI, he worked in various functions and capacities for Quantum Reefs, and his areas of interest include renewable, large-scale integration of RE into power grid, CDM, sustainable development, T&D technology, smart grid, formulation of standard and test techniques. Industry Institute interaction is one of his prime area of activity. He has 15 patents, 11 design registrations, more than 50 papers, and has delivered over 100 lectures, training sessions. Dr. Rajamani, with more than 3 decades of expertise, currently mentors as chief consultant and advisor for Reliance Infrastructure Limited. At Reliance, he was involved in implementation of SCADA RMS and guided the electrical group working on distribution, transmission, and generation projects. Also, he has set up power quality measurement and monitoring cell in Mumbai distribution facility. Earlier, for over 20 years, he was with Tata Consulting Engineers, Bombay, and was involved in design of electrical systems for thermal and nuclear power plants and static bar compensators for rolling mill application. He has conducted more than 130 hardcore technical courses. I sincerely hope that we will experience a good discussion in today's session and look forward to your active participation in future too. Please do participate in the survey on apqi.org. Before I hand over to the esteemed speaker, a few housekeeping points for the attendees. This is a VoIP protocol, that is voice over internet protocol. So kindly use mic and speaker, and you can use your headset, and you will be hearing better. So using headphone is recommended for better audio clarity. All participants kindly use good internet connectivity so that you will get a smooth flow and continuity of the webinar. Please submit questions and comments after both the presentations are over via the chat box in your panel. And in case you face any technical glitch, please drop a message through the chat box and it will be attended. So with that, I hand over to our first expert, Dr. Venkat, to present on this topic of today. Thank you.
As far as reactive power compensation is concerned, as we are
now he's going to ask him. He said, the conference is
Can you hear me now?
Yes,
Can you hear me?
I can hear you.
Yeah,
I can
okay.
hear you.
I'm sorry, I believe there was some issue with my audio system. You can hear me all now?
Yes, please carry on.
Okay. As I said, reactive power in the elementary form is nothing but energy oscillation between two dissimilar energy storage elements. That means you have an inductor and a capacitor. You put some initial energy in one of them. They keep just oscillating the energy, assuming it's a lossless system. It's an ideal inductor and capacitor and connected with a wire of zero resistance. And this is essential to any electrical power system, especially an AC system. As I said, you cannot imagine a world without transformers and motors, and both transformers and motors do require a magnetic flux, which means a magnetizing current, which means an inductive wire. But the issue is, it's not that reactive power is bad. It creates some problems. For example, in the previous circuit, you saw a capacitor and inductor connected together very close by in an ideal lossless circuit. And there's an energy oscillation which goes for infinite time. You have a sinusoidal oscillation. But in a practical electrical power system, you just don't have inductors and capacitors. You also have associated resistances in the circuit. The self-resistance of the inductor, the self-resistance of the capacitor, and the resistance of the wire which is connecting the inductance and capacitor. So whenever the energy flows back and forth between the inductor and capacitor in the form of a current flowing through the connecting wire, there are losses in the system. And because of this, the sinusoidal oscillation damps down. So you have a damped sinusoid and the energy is dissipated. So what will be the energy you start with? Half CV square on the capacitor or half Li square on the inductor. After a few oscillations, maybe a few cycles, you will have the energy which is totally dissipated. This brings us to the basics of reactive power compensation. In most cases, the inductor, what you saw would be the load, because most of the loads are lagging loads or inductive loads. And the capacitive equivalent circuit would be most often a synchronous machine or even a static condenser which is generating the capacitive wire. And this current would be flowing through the entire T&D network, which is not really required because it leads to a lot of losses. Instead, if you can connect a capacitor parallel to the inductor, which is very close by, and make these energy oscillations as a local oscillation, so that the inductor does not have a necessity to oscillate with the capacitor which is far away, the inductor now starts oscillating the energy with a local capacitor. You reduce the losses in the T&D network. This is the basics of reactive power. And you know the very famous equation, the total power what we deliver to the load is the product of volt ampere into power factor, which is the cause of angle between the voltage and current. Let's park it there and move on. And as we know, if there are reactive power, if the power factor is not unity, you know that the current in the system will increase. So the first implication would be there will be increase in current, because for a given power which we need to deliver to the load, because power is what we need at the end of the day, the real power which can be converted into a useful work like a mechanical energy, electrical energy, heat energy, light energy, chemical energy. For a given real power, the current what we need to deliver increases as the power factor comes down or the reactive requirement of the load goes up, which means there are increased currents. And increased currents automatically imply increased losses. These are ohmic losses. Whenever there's a current flowing through a non-ideal resistance network or a conductor, there will be an I square R loss. And if you have increased losses in the system, you have lower energy efficiency, which means higher operating cost. I mean, depending on the report you look at, the T&D losses could be anywhere between 8 to 30%, and that's a higher operating cost. And if you have a higher current, not only you have a higher energy loss or a lower energy efficiency, there's a block capacity. Because each of these equipment in the network, be it the cable, the conductor, the transformer, the switchgear, are rated to carry certain current. And instead of carrying real current, if you're going to be carrying reactive current, you're blocking the volt ampere capacity. For example, a 100 kVA transformer cannot deliver a 100 kilowatt load. Maybe this delivers only 70, 80, or 90 kilowatt load, which means I need to rate the transformer for a higher volt ampere, which means a higher investment. And whenever we have losses in the equipment, you also have additional heating. And as we know, any electrical insulation, which could be a polymeric insulation or an oil paper insulation, whenever there's an additional heating, the operating temperatures go up, which means there's a loss of life or a lower reliability. Depending on the type of insulation used, it could have a 8-degree rule or a 10-degree rule, which means for every 10-degree increase in operating temperature, the life reduces by almost half. And of course, you have lower voltage stability margins, because whenever the current from the generating station flows through a series impedance comprising of resistance and reactance, there will be a voltage drop. So the receiving end voltages will be much lower than the sending end voltages. So even if the alternators are generating 11 kV at the receiving end, it could be much lower, which means I have a lower voltage stability margin, which has got its own secondary and tertiary effects. Like if you have a lower voltage, then the motors tend to draw a higher current. So these are the 5 major implications of reactive power in the system, which are very well known. Apart from that, you have certain other implications like failure of equipment or malfunction of equipment. Over the last 25 years, I've seen quite a few cases where people have reported equipment malfunction or failure because of low power factor or a combination of power factor and harmonics. You have poor operational efficiency or unplanned outages. It could have neutral burnouts. You can have under voltage conditions, which could lead to cascaded tripping, or you can have a poor operational efficiency. There are also cases I've seen there is poor quality of the products manufactured. In a classical automotive welding shop, when you do a spot welding, you actually create a temporary short circuit, which means you need to pump a lot of energy to melt the metal. But if the voltage is going to dip, then you'll never have a proper melting, which is equivalent to a dry soldering. So these are some of the effects of reactive power. And of course, last but not the least, you have damage to equipment and personnel. Now the flip side of that is, or the other side of this story is, when you do reactive power management or reactive power compensation, the benefits are much easier to visualize. Yes, of course, there will be a reduction in current, which means there's a reduction in block capacity. You don't have to have a higher volt ampere rated current, higher volt ampere rated cable or conductor or transformer or switchgear, which means I can go for a smaller transformer, which is deferred capital or avoided capital. When you have a unity power factor, you have a less reactive power demand, your demand charges do come down, especially in a country like India, where it's a 2-part tariff. You have an energy tariff and you have a demand tariff. You can save a lot on your demand charges. In some states, some countries, of course, you have special incentives and penalties for low power factor. So if you are improving the power factor, either you can avoid a low power factor penalty or you can get an incentive for maintaining a higher power factor. Like when the currents come down, which is the first effect, there will be reduction in losses, which means operating temperatures come down. Not only in India, in quite a few countries, it's been documented that one of the main reasons for distribution transformer failure is overloading, leading to excess heat of the oil paper insulation and eventual failure of the transformer. Such cases can be avoided. You have reduced damage to equipment and improved life of equipment. You have an improved voltage profile. For example, I know a couple of utilities where they went for a statewide installation of reactive power compensation system, not so much to reduce the T&D losses, but to improve the voltage profile. India still has a classical low voltage problem where in some parts of the country, even today after 6 o'clock or 7 o'clock, the tube lights don't come on because they don't even have the strike in voltage. Voltages could be as low as 160 volts, which you can witness even today. So by adding these shunt capacitors, the voltages even at the remote feeders can be boosted up, which means even a simple equipment like tube light would operate properly. And of course, you have tax benefits. Some of these capacitor banks under the energy efficient or energy conservation devices are eligible for accelerated depreciation benefit, which is a lot of tax reduction. And in some specific cases, if there is a statewide or utility-wide reactive power management system leading to reduction in the T&D losses and reduction of the carbon footprint, people have even gone in for voluntary carbon emission reduction or carbon credits under the CDM mechanism. This is very clear. These are some of the benefits, which means dollars to the end user, which is basically could be an industrial user, could be a commercial residential complex. Now let's look at what are the benefits for the utility. For example, if you have lower currents flowing in your T&D network and your transformers, you have a lower T&D loss. So whatever the reduction in the T&D loss, which means that many number of real units are available for sale, which means you have a higher profitability, which is the need of the hour for the Indian utilities. Also, it means deferred or avoided investment in generation. You don't need to go on adding generating capacity because whatever the watts you are saving out of T&D loss reduction is now available for sale. And deferred investment in generation is not only saving cost, it's saving the fossil fuel. Even today, you set up a generating station, you have issues of coal linkages. You don't get coal, you get only scam. So when you reduce the T&D loss, that's an artificial way of increasing the generation capacity and meeting the societal needs. Then you have a release of block capacity, which means the transformers can handle full kilowatt power as much as the nameplate kVA, which again means deferred or avoided capital investment. You have a better voltage profile, means more satisfied customers. Even a basic customer whose tube light doesn't come on will be very happy because his tube light does come on because he's got a better voltage profile. Of course, as I said, utilities can also go in for carbon credits, which means higher profitability. You can trade carbon certificates and also better social status. In fact, some of these are under the corporate social responsibility umbrella. In some cases, you can even avoid a cascaded tripping And reactive power management is one of the essential elements of emergency restoration, a key thing for the utility. And of course, when there are lower currents, lower losses, you have lower heating, lower operating temperature of the distribution transformers, which means a longer life and better asset management. This is well known, utilities would be much better off. Now let's change gears and look at the fundamentals of reactive power before we talk about reactive power compensation in harmonic environment. This is a classical quadrangle where you have a voltage axis, you have a current axis which could be at any angle to the voltage axis depending on whether it's an inductive load, resistive load, or a capacitive load. Now let's move on to the next slide, and you have the classical equations. We know that the real power designated with the letter P is the product of voltage into current voltampere into power factor, which is cos phi, where phi is the angle between the voltage wave and the sine current wave. Whenever we say the angle between the voltage and current, we still talk about the fundamental voltage and the fundamental current, which is the key here, because in a harmonic distorted environment, this could have a slightly different connotation, as we would see as we progress along. Then we have the classical triangle, that we have the power, real power, reactive power, and the apparent power. And you have the famous Pythagoras theorem, which takes you to the apparent power as the square root of real power square plus reactive power square. And based on whichever mathematical equation you want, there are various equations for reactive power, for power factor. You can say cos phi is ratio of real power to apparent power, which is kilowatt by kVA, or you can say it's root of P by P square plus Q square, or cos inverse of tan inverse of Q by P. I mean, these are just the same mathematical equations. But the key today is, what is the primary purpose of reactive power compensation? All these days when people were working on a true balanced, true sinusoidal power network, then the primary purpose of reactive power compensation was to improve the power factor by reducing the phase angle between the voltage and current by injecting a reactive power into the circuit. This is very classical definition of reactive power compensation, when the systems used to be balanced and voltage and current used to be sinusoidal. Let's see what happens. Okay, before that, there's a very famous beer cup or a beer mug where you have active power, which is the beer for which you're paying, and you have the reactive power, which is the froth. I mean, of course, this includes some of my German colleagues who like beer with a froth, that you've got a larger portion of the glass which is filled with froth, which is occupying the space, but you're not keen on paying for it. To the right, what you would see the classical, the phasor diagram, where you have the real power. You have two apparent powers depending on the phase angle. And what you see QC is a capacitive VAR which we're going to inject to reduce the total reactive VAR, by which the reactive VAR comes down and the phasor angle from phi1 becomes phi2. And this again is a very classical equation where we won't spend much time how to compute the amount of compensation required. So kVAR1 is the total reactive VAR required for the load. Then we have the capacitive VAR, and kVAR2 is the net reactive VAR required after compensation. And the classical equation can be very simply derived that the amount of VAR required is kilowatt into tan phi1 minus tan phi2. This is again true as far as balanced sinusoidal conditions are concerned. Now let's look at what happens in the presence of harmonics. The previous equation what we saw, where apparent power is equal to a square root of real power square plus reactive power square, gets modified here. As you would see on the screen, I've written S is equal to root of P square plus Q square plus D square. And the G is the new introduction because of presence of harmonics, and it's called as the distortion power. So we not only have to be contending with apparent power, real power, and reactive power, we'll have to now concern about distortion power. And when you look at the equation for power factor, it gets modified. It's no longer P by S, but the S gets changed as P square plus Q square plus D square, which brings us to a new definition of power factor, which is called as a true power factor, which is defined as a product of displacement power factor and distortion power factor. Now, let's look at it like this. So what you now see is the power factor under harmonic conditions, where it's no longer the phase angle between the fundamental voltage and current, but it is something more. So power factor has now two components: a displacement power factor, what I represented with a capital D, and a distortion power factor, what I represented with a small d. And the displacement power factor equation is the same as in the case of a sinusoidal system, but the definition for a distortion power factor is what you would see in this equation, which is 1 upon root of 1 plus THD I square into root of 1 plus THD V square, where THD I and THD V are the total harmonic distortion, current and voltages respectively. And it is interesting to note that you will never be able to achieve unity power factor even if you have 1% voltage or current distortion, because it's 1 plus root of some percentage square. So even if I have 1% THD in voltage, I will have 1.001, which means the entire concept of so-called madness for achieving unity power factor needs to be relooked at. Because if you have a distortion in voltage or a distortion in current, theoretically, we will never be able to achieve unity true power factor. One can still achieve unity power factor in terms of only the displacement power factor, but the distortion power factor would never be 1. It will be less than 1, maybe 0.999, but nevertheless, it will never be 1. So with this as the basic, let's look at how do we do the reactive power compensation under harmonic conditions. So we have to re-question the fundamental stuff, what we agreed upon a few minutes back, that the primary purpose of reactive power compensation is to reduce the phase angle between the fundamental of voltage and current may not be valid anymore. The question now is, under harmonic conditions, the purpose of reactive power compensation is what? To improve the displacement power factor, to improve the distortion power factor, or to improve the true power factor. As you would see, though they are linked, they can also be to some extent, or to a large extent, they can be independently controlled, the displacement and the distortion power factor. So under harmonic condition, what I would submit, it's not just to improve the displacement power factor, it's important to improve the true power factor, and let's see how one can go about by doing so. Before we get into a little more details of reactive power under harmonic conditions, I thought I'll just share with you some of the reactive power solutions. They are much more than what you see on the screen. Basically, there are two major types. I mean, I've chosen to classify them as capacitive hour generator or inductive hour generators. Our primary focus would be more towards capacitive hour generators because most loads are dominantly inductive. So capacitive hour generators are of two types, rotating machines and static hour. And static hour generators could be capacitors, which could be series or shunt. Capacitors could be fixed or switched. When it is switched, it could be mechanically switched or through solid state devices. And when we have converter-based static hour generators, it could be voltage source or current source. And since we are primarily talking about compensating inductive loads, what you see on the next screen are some of the most popular reactive power compensation systems which are used. Of course, fixed capacitors are still very popular, not only in low voltage but also in medium voltage. Then we have mechanically switched capacitors, more often used in medium voltage substations. So depending on the time of the day or depending on the seasonal load, these capacitor banks are manually made on and off. Then we have automatic power factor control systems, which are shunt capacitor banks, which are automatically made on and off, which could be real time or which could be a little slow using mechanical switches. Then we have advanced static hour compensators, which could be fixed capacitors plus TCR, it could be TCR plus TSC. And of course, you have the latest trend, which is active harmonic filters. Now let's look at how do we choose any of them for a given condition. For example, as I said, power factor correction, the basic principle should be based on identifying the cause for low power factor. You know, there are a lot of solutions available. Fixed capacitor, switched capacitor, IGBT based, thyristor based. It is not a dearth of solution, but where we lack, in my opinion, is not in having solution. There are too many of them, we tend to get confused and we don't choose the optimal solution. So in my opinion, the starting point is to identify the cause of low power factor. What is causing the low power factor? Is it because of reduction in displacement power factor or reduction in distortion power factor? After we have identified the cause, then we can choose the right solution. And this is based on a life cycle costing. Any equipment we buy will have various cost elements like the capital cost, the running cost, the installation cost, the maintenance cost, spare cost, and cost of disposal. And in my opinion, every decision, not just an energy efficient motor, not just a two-wheeler with a higher mileage, even for power conditioning devices, the choice should be based on a life cycle cost and not on capital cost. So this one of the prerequisites is that we not only compensate for displacement power factor, we compensate the true power factor, and the choice of the solution from the list what we just saw is based on life cycle costing. And before I get into actually how do you choose, I just want to make a small caution here, because it's not now. Almost 20 years I've come across n number of cases, you know, in double-digit numbers, where customers have got a power factor improvement or a reduction in harmonic distortion by just disconnecting capacitor banks. I can go on and on. It's at least 2 cases a month I come across where, of course, me and my colleagues, we get a job satisfaction and pay by selling capacitors, but I could solve the problem by disconnecting capacitors. Now, it's a very simple case. I mean, I don't want to get into complicated mathematics, but we know that when you connect a simple capacitor bank, this could lead to resonance or harmonic amplification. This could be either a series resonance or it could be a parallel resonance. I've seen both. Though one could improve the displacement power factor by injecting a larger capacity VAR, this could reduce the distortion power factor, which in turn would reduce the true power factor. On the simple test I've seen, you measure the total harmonic distortion in current and voltage with and without capacitor banks. I'm sure at least 1/3 of the cases you would see the harmonic distortion comes down when you disconnect the capacitor banks, especially if these are simple capacitor banks without any series reactors. And recently, I was traveling in the southern part of the country. I could come across at least 3 or 4 classical cases where a customer had a simple capacitor banks, which was installed maybe 10 years back because he wanted to get incentive for power factor. Now the same utility is now penalizing him for increase in harmonics, but he doesn't know what to do. He's got a simple capacitor bank, almost 400 kVAR, and his harmonic distortion was very high. For example, his 11th harmonic was almost 43 ampere. 7th harmonic was 17 ampere. 5th harmonic was 17 ampere. All I did was I just disconnected the capacitor bank, and you saw a sudden reduction in the current. 43 ampere of 11th harmonic came down to 3 ampere. 17 ampere each of 5th and 7th came down to 3 ampere each, which very clearly showed that his excess harmonic distortion, for which he is now paying penalty, is not because he has got a large number of nonlinear loads. He is creating an internal resonance in the system. I've seen THDs as much as about 20% coming down to 10% by just disconnecting the capacitor banks or adding an appropriate series reactor. I mean, you can go into a lot of details, but then this is very well-known concept. Never use a simple capacitor bank in a harmonic-rich environment because you don't know what's going to resonate with what. There are too many inductances and capacitors on the network connected in series and parallel, and you could get into some kind of resonance. Also a caution, whenever you're using a simple shunt capacitor bank with active harmonic filter, it's not to be done at all. Even using a simple shunt capacitor bank with tuned harmonic filter, I would say I would not recommend it, but can be done provided you have an expert looking at it, because there could be again some parallel resonances where it could create a lot of open circuits. Now, this is a classical catch-22, what I was talking about. 20 years back, a lot of utilities started giving incentives for power factor, higher power factor, or penalty for low power factor. So a lot of customers have installed simple shunt capacitor banks to improve displacement power factor. Those days, the meters were measuring, I don't know, but most likely displacement power factor, not the true power factor. And all the incentives and penalties were based on measurement of displacement power factor. So everybody could achieve a unity power factor in terms of displacement power factor. But over a period of time, the entire network got distorted because whatever loads we are adding in the last 10, 15 years, a good portion of the loads are nonlinear loads. Switched mode power supplies. Nobody uses a linear power supply. UPS, inverters, even the fan regulators today are solid state. Dimmer stats, light dimmers, LED bulbs. Even air conditioners today are inverter driven. So the amount of nonlinear loads going up, which means the total distortion in the system goes up. So in most cases, the harmonics are getting amplified due to resonance condition, which could be fortunately a local resonance, within the network and not a global resonance. Otherwise, you can even have a serious cascaded tripping in the power system. And because of this harmonic increase, depending on the state you're paying a penalty for harmonics. So one of the simplest solutions could be in most cases, a mere detuning of the capacitor bank would help reduce the harmonics. I've seen cases where you just add a 7% reactor or 14% reactor, the THD comes down by almost 10-15%. In some cases, I've seen where you're really generating a lot of harmonics, where we have drives inside or inverters and UPS inside. You need a passive harmonic filter. A partial tuning or a full tuning is good enough. And in very specific cases where you have multiple high-frequency harmonics, where you also want to correct for unbalance, maybe you should use a hybrid or an active harmonic filter. Now, this brings us to the key of the topic, that what are the solutions available for reactive power management under harmonic conditions? As we have seen, the first solution that comes to my mind, which is very simple, elegant, and cost-effective, is detuned shunt capacitor banks. So when you have a detuned shunt capacitor bank, it injects VAR and improves displacement power factor. It eliminates harmonic amplification. That means it maintains the distortion power factor. It will not improve the distortion power factor, but it will not make it worse. Then you have the partially tuned shunt capacitor banks, which inject capacity VAR, definitely improves displacement power factor. But being partially tuned, they can also either reduce or maintain the distortion power factor. Then we have in the next category, tuned passive harmonic filters, which not only injects fundamental capacitive VAR and improves displacement power factor, they can actually reduce harmonic distortion and improve distortion power factor, which means they can actually improve the true power factor. Then the last of the league is active harmonic filters and hybrid filters. Hybrid filters are active filters plus a combination of detuned capacitor banks or passive filters. They inject capacitive VAR and thus improve the displacement power factor. They also reduce harmonic distortion and improve the distortion power factor, which means they can improve the true power factor. Now, the approach to do this would be, in my opinion, we need to measure power factor and harmonic spectrum with and without the existing capacitor bank. This would be the first key if anybody wants to do reactive power compensation in harmonic rich environment. We need to measure the power factor and the harmonic spectrum with and without the existing capacitor bank, which will give away any clues as to whether you're having any harmonic amplification. Then we need to analyze the harmonic spectrum, true power factor, displacement and distortion power factor, and identify reasons for low power factor. And as I said, identify optimal solutions. Then estimate the size of the solution required. You know, it is not like a transformer where higher the capacity, better is the reliability, because you could actually end up making a mess of it. You'll have to choose whether you want 100 kVAR, 50 amps, 100 ampere. Then get the detailed specifications of the power conditioning device and evaluate it based on the life cycle cost. So these are some of the solutions for harmonic. As I said, you have the detuned banks, which is 7 or 14%. Then we have partially tuned banks. We have passive tuned filters. Then we have hybrid filters, which is a combination of passive and active filters. Then we have active filters. As you go from bottom to top, the cost per ampere or cost per kVAR goes up. The power loss goes up. For example, if you take a detuned LC filter, the power efficiency could be 99.2, 99.3%. Whereas when you take an active filter, the efficiency could be 96 or 97% or 98%. But as you go up, the harmonic filtering efficiency goes up. Similarly, when you go from top to bottom, the technology and complexity come down. So maybe I would skip this. This only shows various series reactors which are used for partial tuning or detuning, and what are the various tuned frequencies at a fundamental 50 hertz. And this is a generic guideline. You know, whenever there are general rules, I would say people use it with caution, because these are generic. You know, you could have a specific case where this may or may not work. So this is what I generally use. When the THT-I without capacitor, WOC, that stands for without capacitor bank, if it is greater than 10%, then I say use harmonic filters. Otherwise, use standard PFC without reactors. If you have a third harmonic which is more than 20% of the fifth harmonic, that means you've got a third harmonic excess in your system, which means not only you do detuning, use a 14% reactor, otherwise use a 7 or a 5.67% reactor. If the fifth harmonic current is less than 20%, then use a 7%, otherwise use a 5.67, because 5.67 does eliminate a part of fifth harmonic. Okay, this is a typical curve impedance characteristics of a 7% detuned filter, shows why and how it eliminates harmonic amplification, because it's got the lowest impedance at 189 hertz. And normally 189 hertz would not be present in a three-phase AC system. You have third and fifth harmonic, which are 150 and 250 hertz. Now these are some of the aspects related to detuning. Whether you do partial tuning, full tuning, or detuning, the key is the selection of the right L and C value. For example, if you're choosing a capacitor which is going to be connected to the 440 volt system, but if you're using any series reactor, the voltage and the capacitor would be more because of the series inductive drop. That means we need to have a capacitor with a higher voltage rating, considering not only the harmonic voltage but also the fundamental voltage. And if you're choosing a capacitor to be used with a 5.67% reactor, then the capacitor should have a higher current carrying capability, not just 1.3 or 1.5, maybe up to even 1.8 times the rated current, because you are now going to do a partial filtering. And the next is a key. Whenever you have an LC circuit, under certain conditions, there could be a higher current flowing through the LC circuit. Higher current means higher flux density, which means a partial saturation of the inductor, which means a lower inductance. Lower inductance means higher tuning frequency, because tuning frequency is 1 by 2 pi root LC. So when L comes down, the tuning frequency increases, which means from detuning you can go to partial tuning, which means more current would flow. You go back to the first question, you know, more current, higher flux density. You can have a thermal runaway condition. So whenever we choose a reactor, ensure that the reactor is having a very high linearity and it's got a very low loss. And not only this, the linearity, we also look at the tuning frequency as an effect of the tolerance on inductance and capacitance. Whenever we say LC 7% is tuned for 189 hertz, it assumes 100 microhenry and 100 microfarad. But if you look at the standards for capacitors and inductors, they can be made with a specific tolerance. For example, capacitor could be plus minus 10%, minus 5 to plus 10%, or 0 to plus 10%. Similarly, inductance can be 0 to plus 20%. Since the nominal value is where I compute my tuning frequency, but the actual value could be as much as 10-20% off, the actual tune frequency could be very different from the nominal frequency, which must be considered, along with the effects such as linearity effect, the changes in system frequency, or loss of capacitance due to aging, especially in the case of self-healing capacitors. Now let me quickly run through 2 or 3 slides. Apart from these factors, we also look at the linearity of the reactor, higher the better, power loss, lower the better. India today still has a tendency to buy aluminum bound reactors, be it aluminum foil or aluminum strip, which will have at least 50-60% higher loss than copper. So here a copper bound reactor would have a lifetime benefit rather than an initial capital cost. Another key parameter is the intertone voltage capacity, temperature class of the insulation, higher the better, and the correct inductance value. This is the key because most of us are oversimplified life by looking at everything as per kVAR. kVAR is a derived parameter. kVAR is a product of voltage and current, right? So unless you specify kVAR at what voltage or what current, it's a derived parameter. Whereas when I buy an inductance, I buy certain millihenry. I don't buy kVAR. kVAR is incidental. So my request is whenever you choose inductance for tuning or detuning, be particular about the millihenry and the current capacity rather than the kVAR. Now, the other 2 solutions after the detuned or partially tuned solutions, we have fully tuned passive harmonic filters, which can reduce the current distortion to as much as maybe 5, 6, or 8, 10% level, depending on your system impedance and your frequency swings. This can inject VAR at fundamental frequency, by which it can improve the displacement power factor. It can reduce harmonic distortion. There are systems I have built where I could reduce harmonic distortion from as much as 50-60% current distortion to as low as 8% current distortion. That means it can improve the distortion power factor. And of course, it can be single stage, multi-stage, single tuned, or multiple tuned. Then it brings us to the next solution, which are active harmonic filters. They inject harmonics which are synthesized, which are phase opposition to the system harmonics, by which there is an active cancellation. They can, of course, inject fundamental capacitive VAR. That means they can improve the displacement power factor as well as the distortion power factor. They can reduce the current distortion to a level of 2 to 6%. And another advantage with the active filters is, apart from giving capacitive VAR compensation as well as harmonic filtering, they can also correct for unbalance and load currents, and it can reduce neutral currents. I mean, especially if you got a 3-phase 4-wire system, you got excess neutral currents, or all the 3 line currents are not balanced. 10-20% unbalance is okay, but there are installations where unbalance could be as much as 30-40%, where active filters can help you reduce the unbalance. And when you want to select active filters, again, it should be based on life cycle cost, not on capital cost. One of the key issues for active filter is, though it generates reactive power and cancels harmonics, it consumes a lot of real power. If you see, some of these active filters can have an efficiency as low as 95, 96, or 97%. So we normally say the efficiency should be more than 98%, or it should be less than about 20-22 watts per amp. For example, if you go back to the capacitor, which is very, very efficient device, capacitor is one of the most efficient devices. On every purchases, be it industrial, utility, tendered or untendered, they say the watt loss must be less than 0.2 watts per kVAR. 0.2 watts per kVAR is 0.9998% efficiency, right? Whereas when we buy an active filter, which is much more lossy, nobody seems to be interested in specifying the watt loss. In our estimate, it should be less than 22 watts per ampere. Then harmonic attenuation efficiency should be at least 98%. Otherwise, a passive filter would do the job, because passive filters can reach as much as 96% harmonic attenuation efficiency. And if you got a 4-wire system, then the active filter should be capable of correcting unbalance also. And the most important is the sizing, the last line, where you should have harmonic data without capacitor banks. Because when you have a simple capacitor banks, it will be very scary. You can have a 40% distortion, which doesn't mean that you end up buying a very big active filter. You remove the capacitor bank, see what is the distortion, buy an active filter, and the rest reactive power compensation could be done with more cost-effective and efficient devices like detuned capacitor banks. This brings to the last slide of the session, where I've listed down some of the solutions. You have simple shunt capacitor banks, detuned capacitor banks, partially tuned capacitor banks, tuned passive filters, hybrid harmonic filters, and active filters. And every column tells you what they can do. Fundamental VAR compensation, yes, all of them can do, and all of them can improve the displacement power factor. The next column is harmonic amplification and reduction in DPF. Yes, if you have a simple capacitor bank, it's possible. You will be able to get a lower distortion power factor, whereas all the other cases, they are perfectly fine. And then if you have a okay, sorry. So on the last line is the recommendation. Simple capacitor banks not recommended, or it's to be avoided. Then all the other things are recommended. As you see, there are shades of green or gray. I don't know what color you're able to see in your screen. The best would be for if you want to do a multiple solution, not only you want to improve the displacement power factor, also harmonic reduction, maybe go for tuned passive filters, hybrid harmonic filters, or active harmonic filters. But if it is only reactive power compensation without much concern for harmonics, then we can use a detuned capacitor bank or a partially tuned capacitor bank. That takes us to the last but one slide. To me, these are some of the enablers. For the want of time, I would skip this, but the last line is the key. My request to regulators and utilities is whenever they are doing monetizing of power factor, either they are giving an incentive for power factor or penalty for power factor, it should not be based on just displacement power factor, but it should be based on true power factor, which is the product of displacement and distortion power factor. And to sum it up, we know, as we just saw, there are lots of solutions available for reactive power compensation under harmonic rich environment. The solutions can be simple capacitor banks, detuned capacitor banks, partially tuned banks, and active harmonic filters. The optimal choice must be based on a detailed system study and customer requirement analysis. The selection should be based on a life cycle cost and not just capital cost. And tariff-related tools should address true power factor and not displacement power factor. With that, I come to the end of the session. Thank you very much for your patient listening. Hello? 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 Hello?
Hello.
Can you hear me?
Hello. Thank you, Dr. Raghavan. Yeah, thank you, Dr. Venkatesh.
Thank you.
We'll now switch over to Dr. Rajamani.
Yeah.
Dr. Rajamani, kindly go ahead.
Sure. Hello. Thank you.
Yeah, please go ahead.
Good evening. Rajamani from Reliance. Good evening. This is Rajamani from Reliance. You had a very good introduction of harmonic filters, fundamentals, and reactive compensation. But to continue with some practical aspects and show your actual harmonic voltages and currents as captured at site. Power quality and custom power, I think these are the two buzzwords spoken very frequently in the power industry. See that? Of course, it depends on where or the utility or the supply. Would not expect to millions of customers to supply power like an UPS. There will be faults in power systems. Whenever there is a fault, there will be voltage dips due to various reasons, and that could be interruptions due to tripping of generators, networks. Therefore, but the utility can, whereas the customer definition could be the characteristic of the power supply should enable smooth, uninterrupted operation of the equipment. Therefore, there is a dichotomy between what the user wants and what the utility can give. And the utility can give a reliable power supply, but what the customer wants is not only reliable but a quality. In many corners, even the 24/7 power supply is not available. But wherever it's available, then the question of quality of power supply comes. Ultimately, it depends on what is the power quality. It can be what the utility can offer, the extent of deviation from the pure sinusoidal waveform of declared voltage and frequency. Only in textbooks. Of course, you can see that the sinusoidal waveform is a dinosaur. It is almost extinct. If you now connect here power quality meter into any socket, I think hardly you will be able to see this type of waveform. So much of distortion from sinusoidal waveform. Who are the culprits who are distorting this sine wave? The culprits, the nonlinear devices. What is the definition of a nonlinear device? Is one in which the voltage and current relationship is no more linear. The examples could be electronic chokes, compact fluorescent lamps, SMPS fixed mode power supply, which of course is present in every laptop and every PC. In the case of industrial plants, it could be three-phase power converters, variable frequency drives, DC drives, and even UPS, which gives a clean output but can create a lot of harmonics in your system. You ask any electrical engineer, the most difficult load to supply is basically, if you can see, arc furnace and rolling mill applications. It has got highly stochastic very high harmonic content loads. The and the third harmonic and even the fifth harmonic, and this is the type of waveform which you get when you are connecting the computer loads. No? Hello? Yes? Okay. Extremely non-linear. Now let us talk of the compact fluorescent lamp. The compact fluorescent lamp, you can see between the voltage and the current. Again, the current is completely distorted. And if you can extract the harmonic component of this, you can see that the The third harmonic is extremely high, and of course the CFL is used very widely in residences now, and now you can see the amount of harmonics we are actually injecting into the system because of the CFL. Of course, now we will come to another lighting equipment even promoted by the Government of India as a mission statement as part of the energy conservation program. Of course, like a cholesterol, we say good cholesterol and bad cholesterol. Therefore, there are good LEDs and bad LEDs. And I will show you the first slide for a good LED and then some slides for the bad LED. And in this slide is a good LED, is a 15-watt lamp of one manufacturer which we have actually captured the waveform. You can see the bottom portion. The current waveform looks reasonably good. Reasonably good. And then if you see here the total harmonic distortion is only around 5%. Therefore, it is an extremely good this one LED where the current distortions are very, very limited. And then if you see the power factor, is an excellent power factor I get, 0.96, almost equal to unity. Therefore, this is a very good LED. But in the market, we also have got some LEDs whose current waveform we have picked up, which you can see at the bottom, etc. is a 10-watt lamp of some other manufacturer. You can see here the current waveform. It doesn't even remotely looks like a sinusoidal. It looks like a simple series of triangular pulses. Therefore, you can anticipate that total harmonic distortion of the current could be very, very high. Yes? Yes, what we say is correct. The total harmonic distortion is almost about 168%. Therefore, this LED has got a very high harmonic content. Not only the harmonics is very high, you can see the power factor. The power factor will be a good power factor for a lamp. If not 1, should be at least greater than 0.9. But this is an extremely poor power factor, and therefore there has to be maybe some regulations when you are introducing LEDs in a very big way about harmonic distortion limits and what is the power factor of operations. Of course, for comparison, I was shown the electric bulb which was invented by Thomas Edison. It is nothing to beat as far as the harmonics point of view, the bulb, because the voltage and current are perfectly purely sinusoidal. But unfortunately, the efficiency of converting electricity to visible light of a bulb is extremely poor. In this area of energy conservation, the bulb is dead. Therefore, in the olden times, when the King of England dies, they used to say, "Long live the king, the king is dead." Now we can say that, "Long live the bulb is dead." Performances require clean, meaning a pure sine wave supply. That is, you want a clean supply for all our sophisticated electronic equipments. But unfortunately, the conditioners themselves are polluted. For example, if you have an UPS supply, the output of UPS could be, a pure sine wave, but the UPS input supply, it can actually pollute the supply. Now, I'm showing us some curves but these are not specifically about harmonics. All electronic equipments are designed to withstand supply. If you see the normal range is around 90 to 110 per. But the tolerance to the over voltage range is extremely 20 hertz waveform. But if we ask the utilities faults can occur anytime, and there will be voltage dip during the fault in which the voltage will go below 70%, and the fault has to be cleared by a breaker whose operating time cannot be less than 20 milliseconds. It will be more than 20 milliseconds. And that is the reason why I appeal to the users that whenever you are buying an electronic equipment, you must specify what is known as the write-through capability. That means that even if some voltage dip occurs on the supply side, your equipment should be able to write through these voltage dips and then come back when the supply is restored. And this write-through capability time should be at least around 200 to 300 milliseconds, so that but it must really come back. That is what is saying. You are cannot expect 100% supply. Sometimes people get confused between harmonics and transients. Of course, this is entirely two different aspects. Harmonics is basically a steady state phenomenon. It is continuously present as long as nonlinear moves exist. The key thing is that transients, when I talk of harmonics, we talk harmonics only of integer multiples, second, third, fourth, fifth, sixth, etc. Whereas when we talk of transients, due to abrupt changes in power system status, like you are closing a line or opening a line, a lightning surge occurs. Therefore, it occurs for a very, very brief moment. We are talking a time in terms of microseconds to milliseconds. Therefore, the thermal time constants are very high, and the transients do not have any effect on heating. And since it occurs very randomly, it is very difficult to locate and eliminate. High frequency, basically transients are very high frequency, maybe megahertz and kilohertz. It corresponds to natural frequency of the system, that is root L by C, where L is the inductance and C is the capacitance, and it has nothing to do with 50 hertz or 60 hertz, which is the power frequency. It is not a function of 2 times 50 hertz, 3 times 50 hertz, 4 times 50 hertz. It has to do with only the natural frequency of the system, which is in kilohertz or megahertz. Other important aspect is that the effect of harmonics, let's say a harmonic current of some amps flow, how does it affect in a low system, a small system and a big system? What we mean by small system and a big system is small system is one in which the fault levels are very low, whereas the big system is one where the fault levels are extremely high. Now, I have given you two examples. One on the left-hand side is a 100 MVA small system. Another is 10 times, on the right-hand side I have shown a 1000 MVA big system. Let's assume that a 10 amps harmonic current is injected at both the systems. Now, in the case of a small system, the system impedance is at 11 kV, that voltage square by 100, about 1.21 ohms into harmonic current. Therefore, the harmonic voltage generated is about 12 volts. Whereas the same harmonic current of 10 amps in a big system, where the system fault level is 1000 MVA, the system impedance is now 1/10 of 1.21, 0.121 ohms, and therefore the harmonic voltage which the 10 amps creates is now 1/10 of what is created for a 100 MVA system. Therefore, and naturally when you go higher and higher voltage levels, the fault levels will go higher and higher, and that is the reason why the effect of harmonics at higher and higher voltage levels is not that much of serious concern as it happens in low voltage systems. Of course, when we talk of low voltage systems, the last mile connectivity is usually at 400, and that is when actually the system size is very small. Just one. And as we say, usually we say that bottleneck is at the top of the bottle, but here in this system, bottleneck is at the bottom of the bottle. Harmonics is generated at local end and felt more at lower voltage levels because of the intervening impedance of the network elements like transformer, lines and cables. Harmonic penetration at EHV level is much lower. This is very, very crucial harmonic pulse. Now, if you see in LV systems, the most troublesome is the third harmonic. I have shown here on the right hand side some figure where in the R phase, Y phase and B phase, it has got a fundamental component of IF angle 0, angle 120 and angle 240. And the third harmonic component, as you know, is actually zero sequence component where the angles are always zero. They are all in phase in all three phases. Therefore, on the neutral when you come, the fundamental component one angle 0, one angle 120, one angle 240 adds up to 0, whereas the third harmonic component adds up to 3 times. That is the reason why when the third harmonic component is high, the neutral current flow is high, and therefore whenever there is a neutral burnout, you can always suspect a huge amount of neutral current flow. That is the reason why you will see that cables, when the evaluation, when you are specifying the cable before 1980s, we used to have 3.5 core cable, where the neutral was half the size of the phase. Whereas after 1980s to 2000, when electronic equipment start getting introduced at the low voltage level, we went for 4 core, where the neutral size is the same size as that of the phase. Whereas after 2000, with proliferation of tremendous amount of electronic sophisticated equipment, we are now going for 5C, where neutral is twice the size of the phase. Of course, to prove the point that at high voltage levels, that harmonic does not have too much effect. This is current waveform taken for a traction load. Of course, you can see on the top, since the traction loads are connected only between your two phases Y and B, you can see the current on Y and B phase only. And then you can see here the extracted current is shown on the left, and we are not showing THD. THD is applicable only for a voltage. We are showing a TDD, total demand distortion, and for this total demand distortion, as per the IEEE, we see for the voltage level of 33 kV and the fault level, it should be less than 8%, but actual TDD observed for this traction load is less than 2%. Therefore, as you go higher and higher voltage levels, the amount of harmonic content which the system can absorb is also higher because of the very high fault levels. And a very exciting topic is basically harmonics versus transformer overload capability. Whenever a transformer feeds harmonic loads, there are two major effects on the transformer. One is the increased copper loss, and another is increased eddy current loss. Of course, increased copper loss is basically because the RMS current itself increases because of it contain not only the fundamental but harmonic component of the current. And the eddy current loss of course also increases because of the increase in frequency, because the eddy current loss is proportional to F square. Now, how do I characterize whether the transformer will be able to supply the harmonic loads? There is an IEEE recommendation, and the figure of merit as given by IEEE is what is known as the K factor. The K factor is, if K is equal to 1, it's a pure sinusoidal waveform. If K is very much greater than 5, then there is a significant deviation from sinusoidal. Of course, you need not worry how to get that K factor, because if you plug in any PQ meter, it automatically, you can read the PQ, in the PQ meter, you can automatically read the K factor. It directly gives you. Of course. Hello? Hello? Yes? System with large background harmonics, sizing of reactors and capacitors to be done more accurately. Of course, filter design itself, as Dr. Venkatesh has pointed out, is a very big topic by itself. Custom power solutions, again Dr. Venkatesh has talked about the passive and active filters. Then reactive power compensations, the conventional switched capacitors, static power compensators. Of course, in a very high networks, we have the flexible, what we call as the fax devices. The switched capacitor, of course, that is the basic vanilla design, where the conventional breakers are used to switch on or switch off the capacitors. And the static power compensators is just a fixed capacitor in parallel with the thyristor controlled reactor. By controlling the current through the thyristor controlled reactor using the thyristor firing, you can continuously monitor and change what is power compensations. Of course, everything in life comes with a price. Therefore, whenever you're using 11 kV capacitor, 33 kV capacitor, 6.6 kV capacitor, whenever you switch, etc., you will see that there are some notches in the voltages. And also, the connected equipments should be able to withstand these type of notches repeatedly. In addition to that, many of the breakers which are connected to the capacitors, they should be able to, the capacitor switching is one of the most onerous duty of the breakers. Many breakers have failed on capacitor duty, and that is one of the reasons why whenever we are ordering breakers, if it is for capacitor duty, you have to be extra careful. Similarly, our conventional APFC, yes, APFC, every time the contactor switches, you can see that one, the notches which are appearing in the voltage waveforms. The connected equipment continuously, if it experiences this, it might experience some problems. Therefore, you have to be very, very careful, and APFC is extremely close to the load center. Of course, this is the last slide. Whenever PQ problems are faced by customer and when it is referred to solution providers, the first instinct is to go for high and fancy solutions. But the problem could be due to simple wiring or bad earthing practices. Simply by improving shielding, earthing, or by providing isolation transformers like zigzag, many of the PQ problems can be resolved. Of course, if the problem still persists, then high-end solutions like surge suppressors, passive filters, active filters, etc. can be considered. But this should be only used as a last resort. As I given in the figure, the ideal strategy is what is shown on the left, and the usual strategy which is shown is on the right. But please try to correct this. First, try to see whether simpler solutions are available to tackle these power quality problems. And before we talk of any power quality problems, first of all, try to get as much data as possible. As much data you collect from the site, then it gives you much more insight into the problem. Thank you very much for your patient listening. Thank you.
Thank you, Dr. Rajamani. It was wonderful, though we had a little bit of problem, glitches about the sound. Now I request all the attendees kindly put your questions. Both the experts are available. Kindly put your questions into the chat box so that we can try to arrange this. The first question is, what are the effect of harmonics on metering system? Dr. Venkatesh, would you please reply to this? Dr. Venkatesh? Okay, Dr. Rajamani, are you there? Hello? Dr. Venkatesh? I think we have some technical issues which was audible during the presentation by Dr. Rajamani. We are facing some challenge in terms of the audio. So Dr. Rajamani, there is a question, what are the effect of harmonics on metering system?
Yes.
Kindly address. you can go on the mic. What are the effect of harmonics on metering system? You are already on the mic.
Hello.
Yeah, please go. Yeah, please go ahead.
The question is the effect of harmonics on metering systems.
Yes.
To be frank, I'm not a metering expert, but the only thing which I can tell is that there are some electronic meters now available in the market, etc., which can measure the really true RMS and the true power. But to give an exact answer to that, I will not be able to give, because maybe I will.
Can you hear me now?
Yes.
I'm unable to answer just now because I don't have ready reply.
Okay, Mr. Manas, this is Venkatesh here. Am I audible now?
Yeah, please. Yeah, you are audible. Kindly address if you have inputs on what is the effect of harmonics on metering system.
Okay, see, there are basically three different types of effects when you talk about metering errors and harmonics. The first one is related to the ratio and phase angle error of instrument transformers. Because when you say metering, there are metering which is directly connected to low voltage. In most cases, it could be higher voltages. So we have CTs and PTs. Most of these current and voltage transformers, whatever be the accuracy class, 0.2, 0.5 or 1, the ratio and phase angle errors are generally measured and qualified at the fundamental frequency using a pure sinusoid. And most of these instrument transformers have a bandwidth of about 500, 600, 700 hertz, not beyond that. So if you got excess harmonics and the wave is distorted, the transformation factors, both the ratio and phase angle error, are much different than what it is quantified for at fundamental frequency. We have seen this problem when we use some standard current transformers for active harmonic filter, which depends on exact reproduction of the harmonic wave with 180-degree phase shift. So if it is 179.5-degree phase shift, actually the entire philosophy is lost. So this is the first error because of instrument transformer accuracies, which could also include the instrument transformers which are inbuilt inside the energy meters. You know, some of them have shunts and some of them have energy meters. The second effect what I've seen is in the shunt operated energy meters, because of the flow of harmonic current, there is excess heating of the shunt. So these are not the CT operated energy meters, these are the shunt operated energy meters. So when an excess harmonics flows because of skin effect, the shunt voltage drop becomes more and it also gets heated, and because of the heating, there is a drift in the resistance value. So for a given current, the voltage drop increases and the energy meter may have a tendency to read little more current. So this is the second error. The third error is basically due to the presence of zero sequence components. This is a very peculiar problem. This is normally, this affects what is called as a 2 wattmeter method of energy measurement. So if you have a three-phase system, if you have a three-phase 4-wire system especially, and if you have a 2 wattmeter method, in the presence of certain sequence components, which could be fundamental or which could be because of triplet harmonics, there could be large errors in reading. When I say large, I'm talking about significantly large errors. I still remember some studies I've done maybe 10 years back where the guy was paying about 1 to 1.5 crore extra energy bill because of these errors, because of sequence components. The fourth type of error, which is very rare but nevertheless could be seen, when you have excess harmonics, and if the energy meter does not have the right electromagnetic compatibility, there could be wrong readings of energy meters because of, I would say, interference. In fact, some of the new age meters have this problem of interference. They have less immunity to radiated as well as conducted noise, and higher the frequency of harmonics, more could be the effect. In fact, erroneous reading of meters was one of the major issues because of harmonic presence. So, I mean, these are, some of the errors. There's quite a big list, but this is what I've seen because of changes in the ratio and phase angle error because of lower bandwidth, increase in the shunt resistance value because of skin effect and overheating because of harmonics, because of electromagnetic interference, and also because of presence of sequence components. These are errors. Apart from the errors, if the energy itself will be more because of harmonics, the power loss would be more. So if the meter is capable of measuring the true power, including the distortion power, then of course that's a legitimate reading. That I won't say is an error.
Okay, another interesting consequential question, whether harmonic generator, that is the consumer, is benefited for recording of energy due to generation of harmonics by them. Basically, the question is wanting to ask that if a consumer is generating harmonic and his recording of energy is done because of harmonics, whether he is benefited. But your earlier response on the metering issue clearly indicates that basically he is at disadvantage if he is doing the recording, and disadvantage also to identify his problem. So if you want to add, kindly add.
See, in most cases, except in the case of sequence components, which depends purely on the phase angle difference, one can even manipulate the 2-watt meter method to read less. But we are not talking about legal issues here. Sticking primarily to the technical issues in most cases, be it because of the drifts and errors, which could be again positive or negative. The phase angle errors could be on one side or the other side. Similarly, the ratio errors can be plus 0.5 or minus 0.5. So it's random. It could be either way. But if it's a shunt operated meter, it will always read more because of presence of harmonics. Because harmonic current through the shunt would create more voltage drops for a given milliohm, right? Because of electromagnetic compatibility, one would never know whether it would read more or high. In most cases, the memory gets corrupted. The meter would even hang, right? So it's very difficult to say. But if you leave out those cases where it could be either way, in general, because of harmonics generation, the meters will have a tendency to read little more. Hello?
Yeah.
Yeah, okay.
Then we have another question.
Yeah.
Life of the reactor is dependent on the insulation coordination and thermal design, etc. Copper or aluminum windings do not influence the loss or life characteristics. Please clarify. Would you have?
It is like this. It's true that the life depends on the operating temperature vis-a-vis the temperature class of insulation, right? For example, you can have an aluminum or a copper reactor, both with a temperature class of H, right? So this is generally true. But what happens is, in the case of a copper reactor, two things happen. For a given reactor dimension based on millihenry current or a given kVAR, a copper reactor will have much lower losses. It will have much lower losses, and consequently a much lower temperature rise, though the insulation class is the same. Ideally, I would like to use smaller and smaller gauges of copper to increase the temperature to go up to the temperature class, but there are other design considerations which limit me doing so. So generally, if you take an optimally designed aluminum reactor and an optimally designed copper reactor, let's say both with class F or class H, the average operating temperature would be much lower in a copper reactor, consequent to the fact that it has got a lower loss, number one. Number two, whenever we talk about aging of an insulation, we are not so worried about the average temperature. We are worried about the hot spots. Now, if you see in a aluminum reactor, we'll be using more aluminum conductor than I would be using copper conductor, because I need to use a thicker section, maybe a much larger winding. So larger the winding, the possibility of a hot spot increases. If it's a smaller winding, then most of the winding seems to be at the same temperature. The temperature uniformity is much better. But as you make the winding larger and larger, there is a probability of a differential temperature rise leading to hot spots. So in a aluminum mount reactor, not only the average temperatures could be high because of higher losses, the hot spot probability is higher, which could mean it could have possibly a lower life, though the insulation is of the same temperature class, let's say class H in both the cases. I mean, does it answer?
Yeah, I think it requires a little more detailing, but this suffices at this point of time. because we are also running a little short of time, and we have number of questions which has come in. The next question comes, what is zero sequence component in harmonics and how it affects? Dr. Rajamani, please.
I didn't hear you. Can you repeat once again?
What is zero sequence component in harmonics and how does it affect? Could you hear me? Okay, I think Dr. Venkat.
Or basically those, for any
No, Dr.
basically
Rajamani,
we have
yeah, please go ahead.
any current, for example, which is not balanced, then it can be split into three components, what is known as the fundamental component or the positive sequence currents, which are exactly in phase in all the three phases, R, Y, and B. That is the reason why when you add positive and negative sequence to the neutral, current is zero, whereas zero sequence currents, if you add, come to the neutral, actually it becomes 3 times. And the third harmonic, if you see, is a zero sequence current, because third harmonic means 120 into 360. Therefore, in all the three phases, it will be 360 degrees or 0 degrees. Therefore, all the three currents or the third harmonic current is called the zero sequence current. That is the reason why when third harmonic currents are present in the system, they add up into the neutral and the neutral gets burnt. That is the reason why we always go for third harmonic filter, third harmonic suppression, etc. Because otherwise the neutral current could be very high. The neutral voltage can shift. It can go up to 2 volts, 3 volts, 4 volts, etc. And I think that this answers your question.
Okay, sir. Thank you. There is another consequential question. The question basically he is asking for the opinion. By improving the neutral earthing of transformer, will it help to reduce the third harmonics level? Let me answer this. Basically, by improving the neutral earthing of the transformer, it won't help reducing the third harmonics level. But the consequence of high third harmonics can be addressed by improving the neutral sizing, as Dr. Rajamani just explained. I think we have just one more question for which we have time. Basically, time is over. We had a little bit of glitch in our sound system. So, if any other question which has come in, what we would like to do that we'll reply that and we'll one question, Dr. Venkatesh, if we can answer this, for initial installation, if somebody wants to choose the detuned filter reactor, what should be the percentage, 7% or 14%? I think that should be the last question. Dr. Venkat, please.
As I said, unfortunately, there are no generic thumb rules, which could be actually misleading. What we normally do is you do a measurement of the harmonic spectrum, voltage and current, find out the source. If the voltage THD is less than 2 or 3% and the current distortion is less than 8 to 10%, first of all, in my opinion, you may not need a detuning, unless there is a specific case where it is warranted. If the third harmonics are less than 20% of fifth harmonics, then I go for 7%. But if the third harmonic current is more than 20% of fifth harmonic current, let's say you have measured 50 amperes of fifth harmonic and third harmonic is about 30 ampere, which means the third harmonic is predominant, then I would recommend 14% and not 7%. And in case where you want to clean up the system of a bit of a fifth harmonic, then we go in for 5.67%, whose tuning frequency is 210 hertz, which is little away from 189 hertz. So It's closer to 250, which means it acts as a partial sink for the fifth harmonic filter. In some cases, for example, if you look at the Indian railways, they don't use 14%, they use 13% reactor. So they don't detune from third harmonics. They are closer to 140, 141 hertz, which means they want to sink in a bit of third harmonic, because if you look at the railway system, they will have a lot of third harmonic. Right, so this depends on the harmonic spectral content, on the source of harmonics, and what is the objective, whether you want to improve just the displacement power factor or also you want to improve the distortion power factor.
Okay, thank you. With that, I think we have already overshot the time. I must thank all the attendees for having the patience. We had a little bit of sound glitch in between. I also thank both of our expert speakers and our NSN partners as well as the coordinator. And with that, I declare this session as closed. Your questions and answers along with the presentations will be mailed back to you in a couple of days' time. Thank you once again.
Okay.
Have a good time.
Thank you, all of you. Thank you. Thank you very much. Bye.
Thank you. Thank you.